Hello, my name is Professor James Spratt. I'm a Professor of Interventional Cardiology at St George's Hospital in London, and I'm going to talk to you today about cutting balloon in calcific disease. So we know that angiogram is insensitive at detecting coronary calcium. And you can see that from this graph, that the calcium that is seen in intravascular imaging is often not seen on the angiogram. But if you do see calcium on the coronary angiogram, it is likely to impact on stent expansion. And you can see that in this OCT study, which showed that if severe calcium was seen in the coronary angiogram, then that translated to a smaller stent area at the end of the procedure. And we know that small stent areas result in adverse patient outcomes. And again, if we look at these risk factors for what causes stents to fail, coronary arterial calcium is right up there and one of the biggest predictors of adverse outcomes. So these balloons, which have evolved to specifically treat coronary arterial calcium, in this earlier iteration it was called a cutting balloon. The cutting balloon was a relatively effective but bulky device. The Wolverine is the latest evolution of that, so the profile is lower, the athertomes are lower, so it is able to deliver to the area and therefore be more efficacious. And if we compare before and after, you can see that the Wolverine has got a lower mid-balloon profile and a lower lesion entry profile when compared to the Flextome, which is the old cutting balloon, or the Angiosculpt or the Scoreflex balloon in this bench studies. And we can also see that the Wolverine rewraps a little bit better than the earlier balloon. And all these factors together should mean that we're able to deliver it to the target site in a more efficient fashion. So I'm going to show you a case which demonstrates some of these features in a typically complex patient. So this is a male patient who's had a coronary artery bypass graft already. Fortunately, that graft has failed to his right coronary artery. And this is the second time he's presented this year with an acute coronary syndrome. The operator who performed the case felt that trying to resurrect this graft is unlikely to be a durable outcome, and he prefers to reopen the right coronary artery. All right, I'm not going to go into details of that, but suffice to say this is done via a retrograde procedure, so down the graft, back up again, with the vessel reunited from an antegrade and a retrograde approach. And where we join the case is that a proximal lesion has been treated with a 3.0mm balloon at high atmospheric pressure. And we're going to have a look at the IVUS runs, which shows a calcific lesion in the proximal segment requiring further modification. So you can see, first of all, the still angiogram, you can actually see the coronary calcium. And we know from our studies at the start that if we see coronary arterial calcium, then that's a significant finding, and it's likely to result in stent under expansion if we don't adequately modify it. You can see that there in the proximal right coronary artery. If we go on to the still angiogram, this is before the recanalization procedure. So you've got a chronic total occlusion of the right coronary artery, and you've got this disease graft which inserts into the PDA branch of the right coronary artery. So you can see, as explained before, we've recanalized this vessel through a retrograde approach. There's a microcatheter that goes down the vein graft and back up the right coronary artery. And you can see this semi-compliant balloon at that precise area of angiographic calcium failing to expand adequately. And here's the intravascular ultrasound from the proximal part of the vessel. On the longitudinal view, you can see as the cursor approaches, the calcium is on both sides of the artery. The wire is in the middle of the artery. And here you've got some eccentric calcium between 12 o'clock and 1 o'clock. But we rapidly move into this area of concentric calcium. And here you've got an almost circumferential or 360 degrees of calcium with failure of penetration of the ultrasonic waves beyond the calcium in the proximal vessel, before it moves into a slightly larger, again, more totally concentric calcium here, no suggestion of any fractures whatsoever, and then more proximally into a large vessel with more fibrotic disease. So let's have a look at that IVUS in a bit more detail. Firstly, distal to this concentric lesion, you can see thin cap eccentric calcium, and that's proximal to the area of high pressure inflation. And this very short but focal area of totally concentric calcium. which the balloon at high pressure has totally failed to modify. So let's have a look at this calcium algorithm for a second and understand where we are with this patient. So first of all, we've opened the artery. We understand what the angiogram looks like. We've done some imaging, and the imaging has identified both eccentric and concentric calcium. And we're suggesting that the initial therapy with high pressure NC balloon has failed to expand this lesion. So what's the next step? Well, we could go on to perform lithotripsy here. We could even consider rotablation. But is there an intermediate step that we could try instead, such as scoring balloons or cutting balloons? Well, let's see. So here is the same IVUS run, but in this case, post-Wolverine balloon. And what we're looking for, if we can see it, is fractures in the calcium, indicating that we've modified the calcium sufficiently to restore vessel compliance and to allow us to implant the stent safely and to a sufficient area. So here's the key area, the concentric calcium, and you can see, although we went through that quite quickly, that there were fractures within it. So we didn't get a chance to look at it carefully enough. So let's go back to the IVUS stills and see if we can demonstrate the calcium fractures to our satisfaction. So here again are the stills. So first of all, we're looking at the more proximal area. Again, you can see fractures at approximately 10 o'clock in this eccentric calcium. But the concentric calcium is completely transformed. You will recall previously that was a ring of calcium with no ultrasonic penetration beyond that. Now in this case, we've got a big fracture at 3 o'clock, which extends all the way around to 9 o'clock. And the cuts here from the atherotomes have disrupted the calcium and altered the compliance of the lesion. And again, before and after, on the left, you've got the concentric calcium. On the right, you've got the modification post-Wolverine. And again, that's very easy to see the dramatic modification of the calcium that's taken place here. More proximally, in the more fibrotic disease, there's also a utility of this technology here. Again, you can see that there's disruption, particularly between 9 o'clock and 5 o'clock, with tears in the plaque itself. And again, that's a good sign that we're ready for stent expansion. But firstly, the patient got an excellent angiographic and result as defined by imaging. You can see the stent expansion is excellent in this still frame. And we very much expect that this will translate to a durable outcome for this patient. So what can we conclude? Well, firstly, cutting balloons work by producing microdissections. The Wolverine cutting balloon is definitely an evolution in the technology. Its main advantage over its predecessor is that it's more deliverable. And we can also conclude that cutting balloons may represent an effective intermediate step, in other words, following conventional balloon failure in the treatment of coronary calcium. Thank you for your attention.